Unlike amplitudes, Polaris is something you're going to be happy to have a problem on because Polaris is really easy. Whether in this video we'll do latitude by Polaris, but azimuth of Polaris is just as simple. You know, Polaris, the pole star, the North Star, is always almost perfectly due north of you. As a result of that, it's always very easy to get a shot of, and that shot is very helpful. For one thing, and people don't really talk about this, but the height of Polaris in the sky is usually almost identical to your latitude. And you can see in this problem we have a DR position of, how well can you see that? A DR position of 25 degrees, 5.7 minutes north, and latitude at a height of 25 degrees, 59.1 minutes north, or 59.1 minutes in the sky. What this means is that if you were completely lost at sea and you didn't know where you were, if you took the height of Polaris and you didn't have any books or anything with you to correct it more precisely, you'd be confident knowing you're something around 25 degrees, 50 minutes north. Like you're in reality, your DR position is further south than that, but not by much. So this is already a pretty close approximation of your latitude specifically. But there are ways to get it more precise. So in this problem, we had our position, our height of our sextant height, and then we've got chronometer error and everything, as well as index error, height of eye. Now, what we're going to need to get to actually perform the Polaris or corrections is going to be your LHA and your HO. So we're going to need to calculate LHA and HO. Before we go through that process, because that process is the same as you've done 1,000 times before at this point, it doesn't need, we'll do it together, but you should probably at that point know how to do it. Let's see, where's the Polaris tables? Here we go. Here are the tables in the book for Polaris calculations. It is the pages immediately before the increments and corrections. So if this is our increments and corrections, you go 2 pages back and you've got all your Polaris stuff. You can see it's organized at the top in columns by LHA, and then there's some correction factors you have to apply that will take you all the way through there. What we need, though, is these corrections are going to be applied to HO, and we start with LHA. So first, we're just going to calculate LHA. So we begin the table like we always do. Zone time, zone description, chronometer time, chronometer error, GMT. And we're going to have zone time 1846, zone description. Where's the calculator? There we go. Zone description, we're in 124 west. So we'll do 29 divided by 60 plus 124, divide that by 15, and we get 8.3. So we're in plus 8 time. Okay. And that will only matter for hours. Then for chronometer time, we have 02 4401. For chronometer error, we have 0215 slow. So then we're going to apply zone description to zone time. We get plus 8. What is that? 20. That's 26, which is going to carry over to 02 the following day. So now we're in the 12th of March. And then for our minutes, we're going to add 15, 116, 4902. We get 51. So GMT here is 251.16 on the 12th of March. We haven't shown a problem like that before, but sometimes you will carry over to the next day. So now we're ignoring 11 and we're going to work with the 12th of March. Then from there, we got to start working on our GHA. So we'll do GHA, hours, minutes, and seconds, and then we'll get our true GHA. And then here, we're going to use our assumed longitude. You don't need a DR longitude. It doesn't need to be that perfect for LHA because we're the whole purpose of this problem is to get latitude. So it's just like any other star site reduction, but we're specifically focusing on Polaris because the work is simpler and it's going to give us our exact latitude. So we'll have our assumed longitude, and that'll give us our LHA. And then we'll be done. That's all we need to do in terms of the book work. So we're going to open to the 12th of March. March 13th. Here we go. March 11th through 13th, right here. And we're just looking for, we don't need the declination at all. We just need, we're working with Aries. Because if you had seen in the book, I forgot to point it out, but the LHA here was not the LHA of Polaris, it was not the LHA of the Sun, it was the LHA of Aries. And because it's not the LHA of Polaris, we're actually not going to need to include SHA at all. We're only working with the Aries value here. So on the 12th, looking for 2 o'clock, you can see the GHA of Aries at 2 o'clock on the 12th was 199 degrees, 38.1 minutes. 199 degrees, what did I say, 38.1? Yes, 38.1 minutes. Now we're going to come to the minutes and seconds, which is 51 and 16. Here's 51 right here, and 16. We go to our Aries column, is 12 degrees, 51.1 minutes. 12 degrees, 51.1 minutes. We'll add those two values together, 38.1 plus 51.1, 89.2, which we minus 60 gets 29.2 minutes. That will add a 1, so that 199 becomes 200 plus 12 is 212 degrees. Okay. Now, we're going to find our assumed longitude, which, well, we'll draw the diagram first. Here we are. We are 124 degrees west, so the Greenwich is like over here. And the sun has a GHA of 212, so the sun is here. So there's GHA, there's longitude, there's LHA. So again, it's going to be minus. Just like always, if we're in the west, we subtract. If we're in the east, we add. So we're going to subtract assumed longitude from GHA. And because we want... Hold on one sec. Let me confirm. LHA, yeah, LHA is to the whole degree. Okay, yeah. Because we want a whole degree value, we're going to set our assumed longitude minutes to be the same as our degrees so that they subtract out to 0. So we're going to set up our 3 meridians. Remember, they're all going to have minute values equivalent, minute values of 29.2. And then we're going to set our possible degree values, which if we are in 124 degrees west, we'll choose this one as 124, this one as 124, or 123, and this one as 125. And we're going to pick which one that our DR longitude falls closest to. And I was confused because I kind of caught on to this earlier, but I wasn't quite aware of it. But our DR longitude is 124.29, so it's actually like right there. Meaning we're obviously going to use this as our assumed longitude, but it also just by pure coincidence, our DR longitude and our assumed longitude are almost precisely the same. Cool. I mean, not critical. It doesn't make a huge difference, but that just makes, it's just neat. So then we're going to have our 212 degree, our GHA and our assumed longitude. We have subtract the two. These are going to come out to 0 here. So 212 minus 124 gives us 88. 088 degrees. We have LHA of 88 degrees. What that means is we can now come back to our Polaris pages. You can see they're arranged with degree of area of LHA of Aries at the top here in units of 10. It stops at 120 here because then we can come over here and can continue. It actually goes on to a third page all the way to 360. But we only need the first page because we've got 80 here. So we're going to pick this column, and we're going to be working everything off of this column here because it's the 80 to 89 degrees of LHA. How this is going to work is you see we have three sets of tables. We have, at the bottom it's listed as A1 through A2. It doesn't actually show, oh it does here. So this is the A0 table, the A1 table, and the A2 table. What this means is that we're going to collect these as three totally separate numbers, and we're going to work with them all at the end. At the bottom of the explanation here, you can see it says the apparent altitude, which is technically HA, but then corrected for refraction. Yeah, which would be HO, except for, because we're working with a star anyway, HA and HO are almost exactly the same. So this will be our HO. What we do is we add all three A values, A0, A1, and A2, and then subtract 1 degree. I don't know why, but you have to subtract 1 degree at the end to finish the table. So how we're going to write that out is we're going to have A0, A1, A2. We're going to put HO up here. And then we're just going to do minus 1 degree. And that will give us at the end our latitude. So to begin with, we need to find our HO. So we're going to do the HS to HO section now. HS, IE, dip, HA, main, HO. We'll get burned through this real quick. Our HS is 25 degrees, 59.1 minutes. Our IE is, our index error is 3.9 minutes on. Our height of I is 42.7 feet, which is equivalent to whatever we'll find it to be. So we come to the first page of the book, the altitude corrections, and we'll see, just lost the page. No, okay. First we'll get, we're looking for our height of I is 42.7, so we have minus 6.3 here. This is equivalent to minus 6.3. So now we apply both corrections. If the index error is on, that means we subtract, so we're going to do 59.1 minus 3.9, and then minus 6.3 gets us 25 degrees, 48.9 minutes. Now we're going to come to our main body correction right here. And you can see for stars and planets, if we have an apparent altitude of 25 degrees 48, we apply another minus 2 minutes. So minus 2.0 minutes. And that will give us 25 degrees 46.9 minutes. So there's our HO. We'll carry that over, 25 degrees, 46.9 minutes. And now we're going to find what our A1, or A0, A1, and A2 are. Here we go. Okay. So we take our 80 table. A1 is just the, or A0, sorry, is just the ones place of the LHA. So our LHA was what, 88? Yeah, 88 degrees. We're using the 80 to 89, but then if you see here, it shows all of the possible differences between the two. So here is 88 degrees. So if we follow that column back, or that row back to our column, you could see that our A0 value is 0 degrees and 30.6 minutes. So we'll write A0 is 0 degrees, 30.6 minutes. Remember, degrees here for the set of 5, and then minutes over here. Next for A1, it's based off of our latitude. So remember, we're still working in the same column. Our latitude is just about 25 degrees, but you can see here we have 20 degrees and 30 degrees. And if we bring that back, it's an option of 0.4 or 0.5. We are technically closer to 30 degrees, so I think we'll go with 0.5. But the difference here is 0.1 minutes, so it's not that big a deal. So A1 is 0 degrees, 0.5 minutes. Then A2, come down here. Remember, we're still using the same column. We just take our month. So we're in March. So if we come to March, that gives us an additional correction of 0.8 minutes. So 0 degrees, 0.8 minutes. Now what we do is we take HO, A0, A1, and A2, and we add them all together, and then at the end, we just subtract 1 degree, and that'll give us our latitude. So we do 46.9 plus 30.6 plus 0.5 plus 0.8. That gives us 78.8, which would technically carry over. But because this is more than 60, we can make it easier for ourselves and just do the minus 1 degree right now and subtract 60. And we get 18.8, meaning our true value would be 25 degrees, 18.8, wait, it would be 18.8 minutes, oh no, it would be 26 degrees. Wait, sorry, I'm gonna go back to the top because I'm confusing myself here. We do 46.9 plus 30.6 plus 0.5 plus 0.8. Get 78.8 minus the 60. We get, oh yeah, that's what we should have done. We subtracted 60 twice. 25 degree, or we would have 26 degrees, 18.8 minutes. However, we want to subtract another 60. We get, well, it's going to come out to 18.8 again. So yeah, I was right. So you remove those 60, and then you're just getting your final value of 18.8 minutes. Sorry for confusing you there, but you add all these values up, then you subtract 60 additional minutes, and you'll get 18.8 minutes, or 25 degrees, 18.8 minutes as your latitude. To review all of this, to do your latitude by Polaris, all you need is you run through to find the LHA of Aries. Let me make note that that's Aries right there. And then you find your HO, all in the same normal process that you would do for any other star. Then you open up to the Polaris tables, and you just pick your column, find A0, A1, A2, based off of either the ones placed at the LHA, the general latitude you're in, and the month you're in. You add all of them together to your HO, subtract 1 more degree, and that gives you your true latitude. So that now if you found that, you wouldn't have to worry about an assumed position or a bare azimuth or an intercept or anything like that. You could just throw down a horizontal line at 25 degrees, 18.8 minutes, and that would be your true latitude, just like you do with LAN. So LAN and Polaris are both very easy ways to get your latitude very quickly.